Alright, so we introduced angular momentum last time. Now we're going to look at it more and also talk about conservation of angular momentum. So first off, if we consider a point on a rotating object, we know, well, the formula for angular momentum we know is the radius vector crossed with the momentum vector. And if the point is on the rotating object, then we know that cross product, you're multiplying two things that are perpendicular, so the magnitude of the cross product is just equal to the product of these two magnitudes. Momentum times r, we know momentum is equal to mv, and we also know that v is equal to r omega, which means that the angular momentum of our point is mr squared omega, and for a point we know that mr squared is equal to moment of inertia, and in general it is true that angular momentum, actually let me write it like this, that angular momentum of a rotating object is equal to I omega. The direction of angular momentum can be determined with the right hand rule, so for rotating this way we curl our fingers that way and then our thumb points in the direction of the angular momentum. Notice if you take a time derivative of this, you get dl dt equals I d omega dt. The omega dt we know is angular. The derivative of angular velocity is angular acceleration. So we get I alpha, and we know the time derivative of momentum is torque. So if we take a time derivative of that, we do get the rotational analog of Newton's second law, net torque equals I alpha. So, for example, if you have a bowling ball of mass 6 kilograms and radius 11 centimeters, set it spinning with an angular velocity, we want to find its angular momentum. Well, this is a bowling ball is more or less, it's close enough to being a solid sphere, and it's rotating around its center of mass, so we can say the moment of inertia is 2/5 mr squared. Remember, you're not required to memorize those, but to save you flipping back through to the formulas, we know the moment of inertia is 2/5 mr squared there. So its angular momentum is equal to I omega, which is 2/5 mr squared omega, and then we can plug in numbers to find the angular momentum of this bowling ball. It's pretty straightforward. 0.2904. Oh yeah, and we should also think about the units. I forgot to mention that. The units of, well, we may not remember the units of moment of inertia, but we can go back to here. MVR, mass, kilograms, velocity, meters per second, radius, meters. So the units of angular momentum are kilogram meters squared per second, which is the most painful unit of anything you'll have to write over the course during this course. It's just a complicated unit, and there isn't a derived unit that's that we change that into. Here's another example of father of mass MF, mass father, and a daughter with mass MD, mass daughter, sit on opposite ends of a seesaw of mass M and length L. Treat the seesaw as a uniform rod. Uniform rod, axis through the middle. Moment of inertia 1/12 ml squared. And we're going to write an equation for the angular momentum of the system when the seesaw has angular velocity omega and is making an angle theta to the horizontal. Well, let's think about this. So we've got an angle. Why is the angle important? Because of gravitational force. Torque. Seesaws are supported in the middle. And then you've got, the two people sitting on opposite ends of the seesaw. Our angle theta to the horizontal occurring. So what forces do we have in this system? Well, we've got gravitational force acting on this person, gravitational force acting on this person. But actually the forces don't matter for the angular momentum of the system. Yeah. Angular momentum of the system, well, we know angular momentum is equal to I omega. Moment of inertia, we have a rod and 2 point masses. Times omega. So the angular momentum of the system, we can pull out stuff and, well, I guess we can't add fractions, but we can pull out an L squared, got an omega, got an L squared, and that leaves us with 1/12 big M, 1/4 mass of father, 1/4 mass of daughter. So this is an expression for the angular momentum of the system. Excuse me. And if we want to find the angular acceleration of the system, well, then we can take a time derivative of the above equation. If we do that, we get dl dt equals d omega dt. None of this other stuff is changing. L masses are constants with respect to time, more or less. I guess the daughter and father might be losing weight as they do this, whatever. But dl dt we know is equal to net torque. So now we need to figure out, well, what's the net torque on the system? Well, we know that net torque comes from gravitational force on each of these two thingos. So in the, let's just say that the dad's over here and the daughter's over here, or not dad. So this is father, this is daughter. Dad and daughter both start with D, so that's not, yeah, father, daughter. So the father produces torque in the counterclockwise direction. That torque is equal to mass of the father times G times L over 2 times sine of theta, sine of the angle between that force and the lever arm, which is this. Right, well, if that's theta, that means the angle between the force and the lever arm over here is 90 minus theta. The daughter produces torque in the opposite direction. The angle between that force and lever arm is also 90 minus theta. We know d omega dt, that's our angular velocity. And so we can write, we've got an expression now, a factor of L cancels. And we've got this big nasty expression, alpha equals, we've got a G, sine of 90 minus theta is cosine theta. So we have mass of father minus mass of daughter, 1/2 cosine theta, oh G, whoops, don't forget the G, G cosine theta. And then that's all over this big nasty thing over here, L times 1/12 M plus 1/4 mass of father plus 1/4 mass of daughter. And I want to make that a little bit nicer, so we could multiply numerator and denominator by 12 just to make things a little bit nicer. So then we have 6 mass of father minus mass of daughter, G cosine theta over L times M plus 3 mass of father plus 3 mass of daughter. The multiplying by 12 isn't necessary, but there's our expression for the angular acceleration of the seesaw. And this is presuming that they're rotating on the seesaw and presently not pushing off of the ground. Yeah. Conservation of angular momentum is one of the fundamental conservation laws of the universe, as far as we can tell. That the angular momentum of the universe remains constant. And why is that? Well, net torque is equal to dl dt. So, well, L is angular momentum. So when is angular momentum conserved? When the net external torque is 0. Could there be an external torque on the universe? Well, the universe is all a physical reality, so in order for there to be an external torque on the universe, that would have to be something coming from beyond physical reality, and would therefore be kind of by definition an act of God of some sort. So angular momentum seems to be one of those laws that God has set in place in the universe that can only be violated if he decides to do something about it. Yeah, so that is one of the quantities of the universe that is conserved. But for a given system, it's conserved when net external torque is equal to 0. Just like, remember, our linear momentum, regular momentum, was conserved when net external force is equal to 0. So there are multiple ways that angular momentum is conserved. I have a couple of demos that are kind of cool to show you that, and I'll have to do those during your next class when I am there. But this, you have probably seen skaters and divers. You've seen people do figure skating or do diving. Less so diving at YIS because the diving boards are really close to the pool. But like high divers, Olympic high divers, how do they use angular momentum? Well, if angular momentum is conserved, is there an external torque on them? Well, I guess, if you flail your arms through the air, you're getting a little bit because you're pushing some air, so you can kind of torque yourself a little bit, but not the same way you can if you're like in water. There just isn't enough resistance from the air to do much. So angular momentum is basically conserved once the divers jump or the skaters start spinning or whatever. So how could they change their rotational speed? So we change moment of inertia to change omega. What do skaters do? Well, they start spinning, and you've seen them. They tuck in their arms close to their body. And what happens? They spin faster. Well, by tucking, the tucking moves mass closer to the axis of rotation, thus decreasing moment of inertia and increasing angular velocity, or vice versa. Move the mass farther out to rotate slower. So you've seen skaters do that. They tuck their arms in, they spin really fast, it looks cool. And then when they come out of that spin, they kind of spread their bodies out again so that they can keep themselves under control as they start to move, so they slow down their angular velocity again. Likewise, divers, right after they jump, they usually tuck in some way so they can spin faster. And then right as they're about to enter the water, well, number one, they want to not make a big splash. That's part of it. But they untuck then to slow themselves down so they can enter the water at the angle they want to. Yeah. So that's why that works, is because of angular momentum.